All right, we need to get started. So the very first thing I wanted to talk about is where people are in the homework, because I know there are problems toward the end that we haven't had a chance to cover yet. So I want to set expectations of trying to see how people are faring. The last few problems may find their way to homework 2 rather than staying on homework 1, given that we didn't cover all that material before the end of class Friday. So that may happen. If you've already started those problems that end up being moved, don't worry, they will still be due, just a matter of the due date. I don't want you to waste your time on something that's not graded. So we were starting to talk about the process of converting an NFA into a DFA. And then the other algorithm we're going to talk about is minimizing a DFA to make sure there are the fewest states possible in the resultant diagram. So we went over the intuition for this last time. Are there questions? Do people want to talk about where they are in the homework, how they feel about the homework, just to give me that level of feedback of how has this homework felt so far? I will have office hours for a couple hours after class. You're welcome to swing by and ask questions. I'd be happy to help you with some intuition to get started. I think that can make a lot of difference.
For the first problem, for the arguments you want, what exactly, like, do you want us to write out why it intuitively makes sense? Or like,
Yeah, whenever something says show, I'm not looking for a mathematical proof, which is why I don't assign things that say prove. If something just says show, then I'm looking for some kind of intuitive argument. Does not need to be a mathematical proof, but I'd like it to be a sound intuitive argument as to why does this make sense to you, and tie that back to logic. I don't remember exactly what that first problem was off the top of my head. So if that doesn't answer your question, let me know what the problem is, and I can give a nudge toward the intuition and or the notation, the appropriate notation for something.
I did have a question about 7B. I just needed to know what the subscript meant, because I know that there's times where there's like superscript, which made sense, which was like exponents and stuff.
Yeah,
But I didn't know
usually subscripts are numbering something. What was the context for the question?
I think it's like n sub a, and then like in parentheses like w.
Gotcha.
It was, let's see.
It was the number of A's in the substring is how I would interpret that. So it's counting the quantity of A's.
Okay, which is kind of similar to the exponent thing, or no?
The exponent thing is usually repetition.
Okay.
So yeah, that's I probably should have specified that. That's how the book says things like the number of A's in something or the number of B's in something. So I think that problem was saying like the number of A's are greater than the number of B's.
Yeah, I'll just goodbye for office hours. That one to me is like still, I'm having a hard time. Just into the understanding what's going on.
Yeah, that invitation goes to absolutely everybody, even if you have what seems like a very small question, I would be happy to answer it. So don't be shy of office hours. I love getting to know you and helping you out with problems. Anything else before we dive into content? All right, so we talked about the process of this. So we asked a few questions about how DFAs are related to NFAs. So it made sense that one DFA could have many potential NFAs that represented that diagram. Then we talked about the logical converse. How many DFAs can we draw for a particular NFA? And the answer is exactly one. There was only one DFA that mapped to that. So because of that, we can construct an intuitive argument about how to transition from having an NFA to a DFA, which is very useful. So the intuition was After a DFA reads a string, how many possible states can it be in? And the answer is exactly one. And with an NFA, how many states can it be in? It could be in any or all of them. We don't actually know. So we need some way to map the set of states that you could be in the NFA to a single state in a DFA. So did we go over all of these? I think we did. Talked about the number of possible states in the associated NFA from a particular DFA. It was 2 to the number of states in the NFA for constructing things in a DFA where each of the possible states is some subset of the states in the NFA. So if we had 3 states, Q0, Q1, and Q2 in the NFA, then we would have 2 to the 3, 8 possible states in the DFA. Not to say that all of them have transitions into and out of them, but that is the maximum number of states that we could see in the associated DFA. Each one of those states represents some subset of the number of states in the NFA. So here was the example. And so we came up with 8 possible states that we would need to make for this. And it turns out that we don't need to make all of them. But I think this is the problem that we left on. So I gave you a couple of starting points here. So since the initial state in the NFA is Q0 and there's no way to get to anywhere except for Q0 without reading a character, then Q0 is also going to be the starting state for the associated DFA. So the possible states in this DFA, we have we have basically the lambda set or the empty set represents where you would be without reading any characters. There's no way to be there. This can also be a trap state. You can also call this the null state. Then there was Q0, Q1, Q2. There's the Q0, Q1 state, Q0, Q2 state, Q1, Q2 state, and the Q0, Q1, and Q2 state. And if we count these number of possible states, we end up with 8. 2 to the number of states in the NFA. So this is the biggest possible DFA we could have for this NFA. We will not need all of these states. So there's no purpose to draw them all out in advance. The best way we're going to be able to do this is by figuring out, okay, what is the starting state? And then say, all right, from this starting state, we can either read an A or we can read a B. What are those associated transitions? And you're going to continue doing this process until you've built a total function. So let's take a look at precisely how this might work. We know that we're going to have some state Q0 that is going to be our starting state in the DFA as well. Because there's no way to get to any other state with a lambda transition in this NFA. If there were, then we could be starting reading the string from any of that subset of states. So we'd still want to make this a single state, but we would want to make it one of these combination states, whichever are the subset of states that you could be in when you start reading the string. Does that make sense? Can't tell if that's a yes or blank stares or it's Tuesday, which is really Monday. So now the question is, we want to figure out what happens when we transition from this state reading an A. So when we read an A from Q0, where could we end up? Q1. We can end up in Q1. But there's also a lambda transition from Q1. So we could reasonably end up in Q2 also after reading an A, just by doing an additional transition without reading a character. So the transition from Q0 on reading an A is going to be to the set of possible states that you can reach when consuming that character. So we're going to call this state Q1, Q2. I'm gonna give people a little bit of time at this point to finish this off. One thing to note is that if there are no such states that you could reach from the NFA, you will want to transition to this state, kind of the null state, which should be your trap state, because you cannot be in any possible state, which means that you must reject the string according to the NFA's rules. Take a few minutes, see if you can polish this off, talk to your neighbors. One thing I forgot to mention is this is the final state. And it's a final state because at least one of the states that's in this set is also a final state. So anything that includes a Q1 in it is going to be final in the DFA. Almost done. Who wants to walk me through finishing this off? Is this currently a total function? No.
So from Q1 to Q2, draw an arrow to Q0 and label it B.
Same arrows on this. Yes, and the reason being, if you're at either Q1 or Q2 and read a B, where's the only place in the NFA you can end up? If you're in Q2 and read a B, you're in Q0. If you're in Q1 and read a B, the only place you can be is Q0. There's no other state that you could end up in on a B. Assuming that you consumed that character, you're restricted to being in Q0. So we make a transition back from this hybrid state Q1, Q2, back to Q0 on a B. There's one more transition we need, I think, unless it creates a new state for us, in which case we'll need to figure out what happens from that state on an A and a B. But from Q1, Q2, what happens when we read an A?
Q1.
Q1, we could read an A, Q2. Who knows? So we could also do that lambda transition and end up in Q2. So it's not just Q1. We could be in Q1 or Q2. So this is going to loop on an A. And that's it. That's the associated DFA. Now we've made a total function. Every one of these has an outgoing edge for an A and a B. And we did not need all of these states. We only needed 3 of them. Do people start to intuitively understand what the algorithm is for doing this process?
I had an additional question, because there is like 2 things. One, there like exists a lambda like input, even though like lambda means like nothing at the same time. But we obfuscated it, or we didn't have it in that Q1, Q2 loop back. would that be wrong if I put a/lambda as like, or like comma lambda as like something that would bring us back to that state, or is it just like known that? We can just leave it out because it's like a blank thing anyway.
It's a good question. In a DFA, we do not have lambda transitions, so we need to remove any possible lambdas from the NFA. There's no way to get from Q1 to Q2 and consume nothing. In a DFA, that's only an NFA kind of thing. So if we consume an A, because a DFA cannot make transitions without reading something, we only need to define what happens when we read something, which is what allows for the creation of these weird Q1, Q2 states. You're just making mappings for the subsets of states in the NFA that you could be in with those associated conditions. Maybe it'd be good to go through an example of how these would read a particular string. What would be an intelligent string to do that for? A, B, A. According to this DFA, what state are we in and do we accept this string?
Q1, Q2, and we accept it.
Yeah, so we're gonna start at the start state. We're gonna read our first A. This is going to be this transition from Q0 to Q1, Q2. We read the B. We're gonna transition back to Q0. We read the A, we're gonna transition back to Q1, Q2. We read the A, we're gonna transition back to Q1, Q2. And what that tells us is if we were to follow every possible path from this in the NFA, we could either end up in Q1 or in Q2. There should be paths to both of those states from this same string. So if we do this, we go from Q0 to Q1 reading the A. So reading an A, we could end up here, or we could end up here, depending on the transitions that we decide to take. Non-deterministically, if there's just a way to get to a final state, we'll accept the string. So far, we are in an accepting state because there is such a possible transition that could lead us to a final state. All right, now we must consume a B. So if we were in Q1, in order to consume a B and not fail, we have to lambda transition to Q2 and read the B to end up back in Q0. So we're back here after reading AB. If we were in Q2, we would read a B and be back in Q0. So in order to read that B, no matter which state we were in, we know that after we consumed the B, we're back in Q0, which we saw in the DFA as well. So this is a good sign that these are reasonably equivalent. Reading a third A from here is very much like reading the first A. We can transition either to, so we know we're in Q0, we can either transition to Q1 or to Q2. So after ABA, we're either here or here, and then we're consuming an additional A, which tells us that if we were in Q2 and did that, we'd be in a failure state. There's no associated transition. If we were in Q1 and read an A, we could either be in Q1 or we could be in Q2. We know we were in Q1 before this, because it's the only possible place we could still be potentially accepting this string. We read an A, we could either end up in this final state or in this non-final state. So we should end up in Q1, Q2, which is the final state of the NFA, because there exists a path to a final state.
Last question.
Yeah.
So, from going from NFA to DFA, typically when just for DFAs with no NFAs involved, we have nodes and they're usually just a single state, like just like one queue. And this one we have, multiple. So that's something that's allowed in making the transition from NFA to DFA.
Yeah, because they represent a subset of the states of the NFA, whenever you could be in multiple of them. And it shows the equivalence between the NFA. The NFA won't have these multi-labeled states, but if the DFA does, it represents a subset of states in an NFA and an equivalent NFA. And that's how you can prove or show their equivalence.
So when we're combining a success, like the double circle and one circle state, how do we like determine whether or not it's like I'm sorry, what's the term for again, when you double?
Cycle, the cycle.
Final state, I think.
Or final state. that-
Okay, I've done the circle, gotcha, that's-
Yeah, it's
Final
blind for some reason. So how do we know if the combined state is going to be a final state or not, if it's like.
Yeah.
it's final?
if at least one of these states is final in the NFA. So we know that Q1 is the final state, so everything that has a Q1 in that subset in these states will be final in the DFA. Because there exists a path to get to Q1 in the NFA to be in any of these states. So if there exists a path, we know we accept. So in the DFA, we know we have to accept.
Okay.
Very good question. Does that make sense? All right, so I think this is finished up. All right, this just walks you through the whole process that we just went through. So if you want to go back and do this same practice problem again, this should walk you through the associated logic to construct the DFA from that I just drew up on the board. Some notes about this, we never ended up in some additional states. States are not necessary. All transitions are defined. The resulting DFA, this should be what I drew. And it is. We ready for a harder practice problem that uses a few more states? Here we go. Start state is Q0. We have a multiple possible transition from Q0, either back to Q0 or to Q1. Consuming a 1, you end up in Q1. With Q1, no matter what you consume, you end up in Q2. And Q2 loops to itself on a 1 and fails on a 0. So what is the associated DFA for this? The very English translation of the algorithm you should be following. That last one. Does everyone feel okay getting started? So how do we get started? How do we figure out what the DFA starting state is? Yeah, we want to figure out what are all of the possible states that you could be in without consuming any characters. So basically, you're looking for lambda transitions out of the start state and the NFA. There aren't any, so the start state will still be Q0. Okay, now we need to figure out, we get from Q0 to potentially some other state, reading either a 0 or a 1. What happens if we read a 0 from Q0? Where could we be?
Q0, Q1.
Q0 or Q1. So we're not going to loop to Q0. We're going to transition on reading a 0 to a new state that is going to be Q0, Q1, which is different from Q0. Even though Q0 is contained within Q0, Q1, we care about the state that is the subset. And since it's a different subset, it's a different state. Now it's a little small to see. This is going to get a little bit large. So from Q0 reading a 1, where are we? Here, the only place we can transition on reading a 1 is here. So we need to transition, we don't yet have a state that is only Q1. So on a 1, we are going to transition to Q1. Since Q1 is final, this should be final, this should be final. All right, now we still don't have a total function. We need to figure out what happens from each of these two states when we read a 0 or a 1. So from Q0, Q1, this state, what happens when we read a 0?
Q2. Wait, which one are we at? Which nodes?
We're at Q0, Q1.
Oh,
We read a 0 to get here.
Yeah.
But now we need to figure out what happens when we read a 0 from here. What are the possible subsets of states? We could either be starting at Q0 or we could be starting at Q1. So if we consume a 0 from either of those states, what are the set of possible states in the NFA that we could be in? Could be in any state. Could be in any of these three states. So we are going to transition on a 0 to a new state that is going to be a final state. Q0, Q1, Q2. Gross. Does that make sense why that is? If you're in Q0, because we have to consider both Q0 or Q1. If you're in Q0 and read a 0, you could be in Q0. If you're in Q0 and read a 0, you could be in Q1. And if you're in Q1 and read a 0, you are certainly in Q2. So by being in Q0 or Q1 and reading a 0, you could end up in any state. What about Q0, Q1 reading a 1? Q1, Q2, we don't have that state yet, so we're gonna have to make it. This is also a final state. That's a very large column. And it's final because it contains Q1. Excellent, so now we've done this, so let's loop back to Q1. We'll treat this kind of like a queue rather than a stack. We're doing a breadth first search rather than a depth first search, adding new nodes. So from Q1, we could either read a 0. What happens from Q1 if we read a 0? You end up in Q2. What happens if you read a 1? You end up in Q2. We're going to simplify this just a little bit and make a single edge to Q2, which is not final. That can be either a 0 or a 1. All right, well, now we need to consider these three nodes in order to make this a total function. Do we see how this process is guaranteed to terminate, first and foremost? It seems right now like it's just exploding in complexity, but an intuitive look at what's happening here, we can't possibly have more than 8 states in this DFA. So this will terminate in a finite amount of time based on the size of the NFA, which makes it a practical algorithm. From Q0, Q1, Q2, what happens when we read a 0? Yes. For the same reason that Q0, Q1 led to Q0, Q1, Q2, it will loop back to itself. We could be in any of the states. We didn't make a new one. All right, from Q0, Q1, Q2, reading a 1, where could we be?
I'm sorry.
From here, transitioning on a 1, we could be in any state. The question is just after consuming a 1 from any state, what is the subset of states that we could be in?
Only Q1 and Q2.
Q1 and Q2. There's no way to transition from any of these states on a 1 and end up in Q0. Luckily, we already have that state, so we can just transition to that state on a 1. I need to really be drawing my arrows here. Is a directed graph. All right, from Q1, Q2, what happens when we read a 0?
Q2.
Yeah.
We can only get to Q2, right? So from Q1, Q2, we're going to transition down to Q2 on a 0. What happens on a 1?
End up back.
Same thing. So we'll add a 1 to that edge.
Yes.
All right. So far, haven't made any new states. This is looking like it might terminate soon. From Q2, what happens if we read a 0? Trap state. There's no possible way that we could be in any of these states after having read a zero. So we will just transition out to a null state. And we know that a null state has to loop on itself on everything. Because there's no possible way to get back into the NFA after you have departed the NFA. All right, what about what is missing now of 1 out of Q2? And that loops back to itself. So Q2, we will loop on a 1. I think that is everything. Do people have any questions about this process? Anything that I've drawn? I know that diagram is ugly.
So I get that it's because like you're using all state, but like if we're just drawing DFA, since Q2 doesn't end up being final state, could we just say that it loops back to itself for the model 0 instead of having it go null state?
In this case, that would be equivalent, but it's not guaranteed to be equivalent, because if there was some way to loop like Q2 back to Q1 or Q0 in some sense, then just the fact that this wasn't a final state doesn't tell you that you can't reach a final state. You can use your intuition to see that once you leave Q1, this entire state is basically unnecessary and you can just replace it with a trap state. But that just happens to be the intuition from this particular diagram. In some potential use case of this situation, you may find yourself utilizing something like this to represent a system, in which case Q2 might actually have some value as a state and shouldn't just be a null or trap state because it is equivalent to it, but it represents a particular state that maybe is an error state or something that's really important for when you transition into this state, send a message to someone saying something went wrong. That is a really good point, though. Other questions? I think I do this correctly. We can make absolutely sure of that in a second. Anyone need this for any other reason? Finishing taking down notes? All right, if you're gonna go back through these slides, here I kind of have the midpoint where you can figure out, all right, I can see how to get to this midpoint and then the final solution once you get to that point. I think this is what I drew. Do people feel like they intuitively understand the algorithm at this point? My recommendation is that you go through this intuition step, because this is what a textbook is going to give you, or this is what it looks like to deliver this in a technical way. And most classes will be writing this notation on the board and go through that process. And I have always felt like this is not how people learn logic or math. You build the intuition, then you show them the technicalities and they can map the intuition they have to the technicality. But this serves as a way to say, it's a fairly simple intuitive idea, but to represent that intuitive idea technically, it can be very unwieldy and kind of scary to look at. But also recognize that what's embedded in this is an intuitive idea that you can understand. Just don't start here. Start at the intuitive level. I've always thought that the correct way to teach proofs is to teach people intuition. Don't teach them the proof at all and then say, well, now construct the proof. And people can actually put it together once they have an intuitive understanding of it. So a good exercise for you at home is to map your understanding of the process that we just went through to something like this and see if you can understand what all of this is saying. Questions on the procedure of converting an NFA to a DFA? Because that is all we're planning to cover with it. But we get to go through an even harder one next. At least what I find to be more challenging. So we're gonna start talking about, all right, we've made this really complex DFA potentially as a result of converting an NFA. How do we know that it is the smallest possible DFA? Well, first, the question we should ask is, why should we care if we have two equivalent DFAs? Why would we care about the smaller one? Or want the smaller one? Yeah, it's efficiency in general, right? You have fewer transitions, which means that it takes less memory to store. It will take fewer, it takes less to represent. It becomes more intuitive if you're looking at a smaller DFA to be able to understand what is the logic of these transitions. You can blow up a DFA arbitrarily large. Given a DFA, you can go through the reverse of this process and end up with something as large as you want. So many possible DFAs that can accept a particular regular language. We've kind of been talking about regular languages and how DFAs represent regular languages, NFAs represent regular languages. So lots of different DFAs could represent the same regular language. So we can determine if one DFA is better than another, fewer states. Leads to either faster termination or less storage space. As an example, here is a DFA. Intuitively, can this be reduced?
Get rid of Q5.
Yeah. So the probably more intuitively obvious thing is there's no way to get to Q5 from the start state. You cannot transition to here. So without there being a single transition into Q5, it doesn't belong in the DFA at all. So we can get rid of all of that. Can the resulting DFA be reduced further?
Just remove the top out and just go through.
So remove this.
Remove the top out.
Remove Q0, Q1, and Q2. And find some way.
Go Q0, go from 0, 1 to.
How do we, for instance, on 0, 0, 0, 0, 1 gets us to a final state. How do we represent that in the final version? It's a good idea, being able to try to remove chunks of the DFA. That will only work sometimes, though. So being able to remove a chunk like this and just say this isn't ever needed.
We could remove Q4 and just have Q2 like Q3 when it has a 1, couldn't we?
So does 0, 0, 1 get us to that point? Yes, because this is still final and that's final, and they both loop to themselves. So if we're in either one of these states, on a 1, we can combine these states into a single state. I like it. I think we can do that. So the resulting DFA now has 4 states. So just one of these states, you can pick one or the other. We'll just transition here to here instead on a 1, and then get rid of this. Now we're down to 4 states.
You could just get rid of Q1 and have Q0 point to Q2 on a 0 or a 1.
But then I guess we still accept 0, 1, don't we? Yeah, you probably could. So we're saying we get rid of this and just add that here because it is equivalent. That's what you were saying before. I think this works. The minimum DFA in this case is 3 states. So you can get there kind of with intuition and logic as long as the DFA is relatively small. Do we agree that if this DFA had 1,000 states, trying to minimize the associated 1,000-state DFA might require a little bit more intuition. And you might be sitting there for a very long time trying to go through all of the possible combinations to figure out if you could combine any subset. How many possible subsets are there when you have 1,000 states? Yikes, lots of possible subsets. So it might be nice to formalize this intuition about how can you start to think about removing some states into an actual algorithm that we can offload onto a computer. So yes, this can be reduced down to that. So let's talk about some things. We need to figure out, we're going to be figuring out if subsets of these states are indistinguishable. So we need to define this concept of indistinguishable. So you have two different possible states. If from both of those states or either of those states, every possible string in the language ends up in a final state or a non-final state. We don't even care about the same transitions necessarily. We just care about whether or not on a particular transition is the resulting state final or not final. If they're both final or they're both not final, then we can combine them. So we can use that same book terminology to say, if any possible transition from state P on a string W is either a final state, so if they're the subset of final states, implies that a transition from Q using that same input string W is also final. And a transition on it is either not final, implies that Q is not final, then they are indistinguishable. So basically, if P on W is final and P on W is not final, implies that Q on W is final or Q on W is not final, then they're indistinguishable. We're going to define the opposite of that, distinguishable, to say there exists some string W such that from one state we end up in a final state, and from the other state we end up in a non-final state. So is there a string that leads from one state, we go to a final state, and from the other state, we go to a non-final state? Those are distinguishable because on that string, we can differentiate between the finality of transitions between the two states. Basically, it's a can we tell the difference question. So we need an example where some transition on a W from P ends in a final state, and some transition from W on Q ends in a not final state. Which one of these looks easier to show and or prove? If I cast you saying you can do one or the other of these, which would you pick? Which one? This one? Yes, this is just find an example. And it says you have to look through every possible transition, not only a transition of length 1, but transitions of length 2, transitions of length 3, transitions of length 4, transitions of length 5. You have to look at all of those and say, for every mapping from one, is it the same for the other? And you have to compare every single possibility. And once they do, you can make these two claims. So this problem, hard. This problem, significantly easier. We can go through some logic. We can figure out if a particular pair of states is either distinguishable or indistinguishable. The whole goal is to find and combine all indistinguishable state pairs. Do I want to go into more than this yet? Probably not. So I think we end here. Does anyone have any questions about this intuition? We'll go over this again at the beginning of class, but yeah.
Just making sure that the if with two Fs, that's like a mathematic term that you.
If and only if,
If and
yeah.
only if, so, yeah, it's been a while since I.
Yeah, F equivalent to.
No, I figured it wasn't. It's just. Well, you know, asking the questions that make me want to sleep in. No, someone's gonna be like, of course. I didn't see it."
Yeah, I'm like, oh.
What is happening?
Yes, which is like, maybe like. Well, also. ABC, and you want to 0 or more. But ABC is not in that. All right.
Sunday off.
Five states here. Maybe this, I don't know, those questions that. Maybe the EFA reduction.
Because and so we have to,